Good afternoon, folks. How are you today? So we are in our last lab, which is Jominy test for hardenability of steels. In the first two parts, 6A and 6B, you learned about the theory and principles and also saw Professor Humphrey doing the Jominy test and collecting the hardness data. So let's see what we have. These are our objectives. We have learned about hardenability of steels. We just conducted the Jominy end quench test on the two steel samples, 1040 plain carbon steel and 4340 alloy steel. We are going to draw the hardenability curves for the two steels. We are going to measure Rockwell indents using Fiji image analysis software. Then we are going to evaluate numerical results, make summary conclusions, and then you are going to submit a professional lab report. Okay, we are following the ASTM A255 procedure. We took the two steel samples. Let me show you what they look like. So this is 1045 and this is 4340. So 1045 of course has 0.45% weight percent carbon. It was austenized at 850 degrees for more than an hour. 4340 steel is a low alloy steel. Of course, 40 means 0.4% carbon. And 43 represents this combination, about 2% nickel, about 1% chromium, and 1/4% molybdenum. Then we used our end quench apparatus to quench it until room temperature. And of course, our cooling rate would be fastest here, water quenched, and slowest here, air cooled. Same thing on 4340. And then a flat surface was machined along the sides. Actually, we machined both sides so that we could lay it flat. And then Rockwell C measurements were done. Okay, so here is my spreadsheet. So as you prepare the spreadsheet and as you enter the numbers, make sure that you use the checksum to verify that your input data is correct. So let me give you a big picture. What we have is we have the Rockwell hardness on the two steel samples, 1045 and 4340. Now on 1045, we made only 14 indents. And on 4340, we have made 20 indents. So let me give you the big picture. What I'm going to do is I'm going to measure only the first 10 indents using Fiji. So I'm going to measure area, perimeter, and then I'm going to process the data just for the 10 indents of 1045. What you are going to do for your assignment is, of course, you are going to make measurements of all 14 indents here. You will find that for 4340, the image contains only 19 indents, not 20. So you are going to make measurements on those 19 indents. So you are going to enter data here after measurements. You're going to enter data here after measurements and then process it just like I am doing just for 1045 alone. Okay. So here we go. We are going to open the 1045 image. We are going to set our scale. Remember, it is 4800 dpi, so we could enter that as well. Or instead of it, we are going to set our measurements. Remember, we are interested in area and perimeter. We are going to magnify the indents as much as possible. Fit an ellipse. We have done this now many times. Measure each indent. You're going to save both the table and the image. Remember, you will have for your assignment two images. I'm working with just one image. And then we are going to transfer the values, these area and perimeter values, to Excel sheet. So let me show you the first few steps. So we are going to fire up Fiji. We are going to open our 1045. Remember, it is already 8-bit, so we don't need to change the image. We can set scale. So I can say 4800 pixel is 1 inch. It actually knows it because it is stored in the header. This is my global scale. Okay. Set measurements. I have area, perimeter, add to overlay, display label, scientific, 5 digits. Okay. And then I'm going to magnify the first indent. And fit an ellipse. Notice I'm using an ellipse and I'm not using the analyze particle type of command, because if I do a thresholding, I won't be able to capture this white area as part of my indent. So that's why we are using this. Another reason why we are using this fitting of an ellipse. So this looks like a good ellipse. Control M. Shrink this. We are going to move to the next indent, which is this one. Fit an ellipse. Control M. And so on and so forth we will do. Okay. Okay, so we have made the measurements. Let's import them into our Excel sheet. So I have this 1045, 10 indents. So I'm going to copy, put them in my spreadsheet. And this is my Fiji worksheet. So name that. Then I'm going to take this area and perimeter, copy, and I'm going to copy them here. Okay. All right. Now that we have the area, what we can do is we can calculate Myers hardness. And you may remember Myers hardness was force, which is 150 kg times 9.8. So this gives us force in newtons. And we are going to divide it by area, which is in inch square. We want to convert it into millimeter square. So we know 1 inch is 25.4 millimeters. So we'll square that. So that's our Myers hardness. We are going to copy this for our 10 indents. Okay, so let's create a hardenability plot. So ideally what you would be doing is you would have 14 indents, and then of course you'll have Myers hardness for 4340. So you'll be drawing 4 curves. I am drawing just 3 curves. So I'm going to select first 3 columns, and I am also going to select this Myers hardness column. Okay, we are going to insert XY data points connected. Let's move the chart to a new sheet, plot number 1. Let's put this Myers hardness on secondary axis. So this is our Myers hardness. This is our Rockwell hardness. Let's adjust some axes. You may remember our hardnesses are somewhere like between 20 and 55. So let's make this 60. No, let's leave it at 55. I would move my Myers hardness curve a little bit. So let's format that axis, and our smallest value for Myers hardness is about 2500. So let's make that 2500. Maybe I'm missing something here. So let's make it 15 then. That's more like it. So point I'm trying to make here is I want to match these two curves. You cannot match them exactly, but kind of somewhat similar. Okay, so you're going to put up the chart title. You're going to format the axes and all that. I'm not going to spend time over it. But remember, you are going to have another Myers hardness curve, which is going to look very similar to the red curve. Okay, so finish it up, touch it up. Okay, so here is our slide for calculating the Myers hardness. And here is the plot we created. So notice I put in the titles and other stuff that you can check out. The key thing was that this is our curve for 1045. Notice the Myers hardness and the Rockwell hardness are very, very similar. There are some differences, but fairly minor. The very interesting thing now is to compare these curves to those published in textbooks. So let's see what you will find in your textbook. So in your textbook, you'll find that your red curve, 4340, is very similar to what we have measured, right? Pretty flat, kind of sloping down slowly. Whereas for 1040, which is very similar to 1045, notice the hardness drops very sharply and then kind of plateaus out here. In our case, our hardness plateaus, falls sharply and then plateaus out. But notice there is a small uptick here. There is a small uptick here also. Before we discuss the upticks, let us consider what is happening to values. So our values here are about 55 or so. That's our hardness of 4340, and drops down to about 50. In our case, our hardness starts 50, kind of goes up to 53, and drops to about 40s or so. But effectively, it is flat for a long time. So this is what is called deep hardening steel or through hardening steel. Whereas here, the hardness is only 44 or so. We expected it to be kind of 50s, and then it drops down very sharply. So this is shallow hardening steel. So initially, here we have martensite, and then slowly and slowly we start getting some perlite. Here, perhaps we could have had martensite 100% or maybe a mostly martensite only through a small shallow layer. After that, of course, we have increasing amount of perlite, and by this time we have only perlite. It is just becoming coarser now. Let's talk about this uptick. The values. The reason why I think the values are lower is because I believe this sample was left at 850 degrees for too long a time, and therefore it has decarburized. So that's why our hardnesses in general are lower, and we have much more decarburization at this quenched end. So when there is less amount of carbon, the hardness is lower. So that's why we see this rising up. When the carbon was low, it could not form martensite because with very low carbon, the hardenability is even poorer. So as hardenability improves, we are able to form martensite, but it is only about kind of quarter-inch deep. Okay, so next step, we are going to plot Meyer versus Rockwell hardness. So let's take 1045. This is Rockwell. We have only 10 points, so that's all we can plot. Select Meyer's hardness. Insert, and we are going to plot the dots. Again, move to new sheet, call it plot number 2. Okay, so again, let's adjust our axes. Rockwell goes from about 15 to 50. You can adjust other things. The key idea here is we expect a linear trend here. So let's fit a trend line. So we want linear, we want to display equation, we want to display R square. So notice our R square is of the order of 0.88, which is a very high linear correlation. So again, you are going to polish up the plot. Put up titles and things like that, and it should look like this. Okay, now we want to get these numerical values of slope, intercept, R square. So just like we have done in previous lab, let's go ahead and calculate that. So we have intercept, take Y values, comma, X values, slope, Y values, comma, X values. and r square. Y, comma, x. Okay, so let's adjust some digits. Just too many digits here. Let's reduce it to about whole number here. Slope, maybe one digit is enough. R square, of course, two digits are more than enough. Okay, so that's our plot two. And of course, for your assignment, you'll again remember you'll be calculating all these indents, all these Myers hardness. So you're going to plot all of those hardness values versus all the Rockwell hardness values. And I am reasonably certain that you're going to get a better line fit because you have much more data. Okay. Okay, the last thing we want to do is the depth analysis. So you may remember that we had a Rockwell hardness formula from which we can extract depth. So our depth in micron would be 2 times 100, which was a constant, minus the Rockwell C value. Okay, so that's our depth. And we can also calculate depth by using the shape of the indenter. So if we use the shape of the indenter and calculate the formula, and we have done it in a previous lab, we are going to take the diameter, which is perimeter divided by pi. And remember, this is in inch. We want it in micron, so we are going to multiply it by 25.4, convert it in millimeters, then times 1,000 to convert it in microns. And then, so this is our diameter, divide by 2, divided by tangent of 60 degrees. So we have to convert 60 degrees into radians, and we'll get our value. So now we have these two depths. We want to compare them. Notice this depth that we calculate from Fiji, which is from the apparent diameter of the indentation, is always larger. And you will find so because of the way the depth is measured by Rockwell indenter. It applies first a minor load, uses that as a reference from which it measures the depth. So you'll always find this to be larger. But the key idea is if it is how linear it is, this relationship. We expect them to be quite linear. So let's plot them. So we will take these two. Let's go ahead, insert, and let's move it to a new sheet. We'll call it plot number 3. And again, let's arrange the axes. So our smallest value is about 100. Here our smallest value is about 150. Maybe 180. Okay, and we can fit a trend line here. And notice this is 0.89, so pretty good linear correlation. Again, you are going to put in proper titles and axis titles, etc. So let's go back to Jominy and let's look at some values. So we have intercept. So these are our Y values. These are our X values. Okay, slope. We expect it to be larger than 1. And then, of course, R square. Okay, let's adjust some. One digit is good there. Slope, 2 digits are good. 2 digits are good here. Okay. So this is what our plot looked like. Again, I'm showing you titles, scale, etc. that you can use. Notice my scale is missing here at the bottom. Probably I didn't copy it properly. But that's basic indentation depth from Rockwell hardness C. And that's about it, folks. Again, I want to emphasize that when you are going to be doing the work with the assignment, you are going to have a lot of depths from RC. That would be your x-axis. You will have a lot of depth from Fiji for both samples. I want you to plot both of them. And again, I am sure you will find a much better correlation than 0.89. Okay, folks, so I have been discussing our results, making conclusions. If you have other observations, feel free to discuss with your TA or me using email. I'd be happy to chat with you. Hope you have enjoyed this lab. And I hope you got a very good overview of heat treatment of steels. Have a good day.